Okay, here's our first example. We have an electric force on an electron by a proton. So as you can see here, we have a proton right there and an electron right there, separated by a distance r. The electron has a charge q1, the proton has a charge q2. So we want to determine what is the magnitude and the direction of the electric force on the electron specifically of a hydrogen atom exerted by the single proton that is in the nucleus. So if you remember from chemistry, uh, the hydrogen atom consists of a single proton surrounded by a single electron. So it's a really great example to use for the electrostatics unit. So if the average distance between the revolving electron and proton is r equals 0.53 times 10 to the minus 10 meters, this is something that we call the Bohr radius. I don't know if you guys remember that from chemistry, but it's the average radius of the hydrogen atom. It's actually a really important distance. Anyway, so remember the value of E. We're going to use Coulomb's law to determine the magnitude of this force. We have Coulomb's law right here with Coulomb's constant times the first charge times the second charge divided by their distance squared. So here, this is the value of Coulomb's constant. Remember, that's 9 times 10 to the 9 Newton meters squared per Coulomb squared. And if you remember the value of E, the elementary charge, oh, let me do that in a different color there. The value of E is equal to 1.6 times 10 to the minus 19 coulombs. So an electron has a negative charge and a proton has a positive charge. Now, it wasn't done quite right here. As you can see, the proton is going to have the positive charge, and there should be a little negative sign right in there to show the negative charge on the electron. And then, of course, you have the radius, or the distance between those two squared on the bottom. So if you calculate that out, you should get 8.2 times 10 to the minus 8 newtons. Now remember, when you're doing this in your calculator, don't forget to put parentheses around each quantity so that you don't mess up the exponents, because if you don't, then your exponents could end up getting wonky in your calculator. So around each individual quantity, make sure you put parentheses. Otherwise, yeah, you're going to have some issues. So if you test this in your calculator and you don't get 10 to the minus 8, it's probably because you used the wrong parentheses or you didn't use enough parentheses. So make sure you try this, practice it, and make sure you get good at doing that. So remember, force is given in the units of newtons. So this is 8.2 times 10 to the minus 8 newtons. Oh, there we go. So what is the direction of the force? Now remember that the direction of the force is dependent on whether we have the same charge or the opposite charge. So we are wanting to find out what is the force on the electron. So that means if we look at the electron, we know that because we have opposite charges, they're going to be attracting one another. So that means, as the picture shows, the electron is going to be forced to the left towards the proton. So we could say, oh, the direction of the force is toward the proton because the charges have opposite signs and the force is attractive. So that would mean the direction of the force that is on the proton would then be to the right because it's an attractive force. So as they're attracting one another, the proton wants to go to the right, and the electron wants to go to the left. Pretty sensible. Let's take a look at the second example. So which charge exerts the greater force? We have two positive point charges, Q1 with 50 microcoulombs. And if you guys remember, the micro, the symbol micro, actually means 10 to the minus 6. So microcoulombs means times 10 to the minus 6. So if Q1 is 50 microcoulombs, then Q2 is 1 microcoulomb, and they're separated by a distance L, such as the figure. So where's our figure? Oh, we don't have the figure. So we want to know which one is larger in magnitude, the force that Q1 exerts on Q2 or the force that Q2 exerts on Q1. So here we have the force that Q1 exerts on Q2. That's equal to KQ1 Q2 over L squared. But then we have the force exerted on Q2 by Q1, and it's KQ2 Q1 over L squared. Now, are they different? Now, they look different, but of course, a property of mathematics says that multiplication commutes. Now, that's just a really fancy way of saying that you can rearrange the order of these two things because they're multiplied together. It's like saying 1 times 2 is the same as 2 times 1. Doesn't really matter what order you multiply them in, it's going to be the same. So Q1 times Q2 is equal to Q2 times Q1. So this is just showing you that the force that each charge feels is exactly the same. So even though Q1 up here, let me find a good way to do this. Even though Q1 has a much larger charge than Q2, it doesn't matter because they both feel the same exact force. It's kind of like when we're doing our gravity unit. Again, remember that charge and gravity are very, very, very similar in the way that their math works. We were talking about the force that you feel from the Earth pulling down on you, and we asked what's the force that the Earth feels from you pulling on it, and they're exactly the same. So just because your masses are so different, it actually doesn't have any effect on the force because the force depends on both your masses. So remember, the acceleration is dependent on your mass as well. So even though you both have the same force, it doesn't mean that you have the same acceleration. So in this case, because the charges, even though the charges are different, they both still feel the same force because the formula is exactly the same. And you can just rearrange the location of those two charges. This is also another way of saying Newton's third law. If you remember, Newton's third law simply says, let me see if I can get my pen. It simply says, different color. It says that F12 is equal to negative F21. So it's the whole equal and opposite reaction thing that we talked about. So the charge 1 feels a force from charge 2, but charge 2 feels the same force from charge 1, just pointing in the opposite direction. So that means if you have two charges that are the same, then they're going to feel an opposite repelling force, but if you have two charges that are different, they're going to feel an attractive force. I didn't draw that very well. Let me try that again. You're going to feel an attractive force like that. Now notice that the directions are technically in opposite directions. So the force of this guy on the top is to the left, and the force of the other guy on the top is to the right. They're in opposite directions, which is what we expect. And down here it's the same. The one on the left is pointing to the right, and the one on the right is pointing to the left. Opposite directions, but the magnitude is the same.